Hello and welcome back to my Applied Data Science channel. My name is Joanna, I'm a senior data scientist and here to share some real-life knowledge from my experience. In this video, we are grouping the customers of an online casino based on their behavior. This is useful in customer profiling in general, as companies can run targeted marketing campaigns and increase the communication impact by addressing each customer group in particular. The goal is to create groups such that the people within the group are similar to each other and at the same time different from the other people in other groups. This is an unsupervised learning problem as we do not know how many groups there are in our data, nor do we know in which of the groups does each one of the customer belong. We are dealing with unlabeled data and we are actually trying to infer those labels by finding the hidden patterns in our dataset. We are using the classical K-means clustering algorithm and learn how to properly select the number of clusters, but this is not going to be the most interesting part of this tutorial video. I will walk you through the steps that I take when performing feature engineering. We are converting time series data of customers to customer features. And here is where the power lies, in how well the engineered features can capture the relevant customer particularities. So let's jump to it. Here I've imported the libraries necessary for running this experiment, pandas, numpy, and datetime, because we are also dealing with time series data. And then seaborn, matplotlib, and yellow brick cluster to do the visualizations. And for the KMeans clustering, we are just importing KMeans from scikit-learn cluster. In a previous video, I've performed exploratory data analysis on this dataset, and I'm going to quickly read in the data and do some data preprocessing, but if you want a detailed analysis, I invite you to watch the full video that I'm linking in the description below. So after doing all this preprocessing, we are here with a dataset that has 3 columns. Under the column customer, we have all the customer IDs of our users. Under timestamp, we have the date and the time at which a particular customer deposited money in their wagering account, and respectively under amount, we have information about how much money was deposited at each of these timestamps. As you can see over here, we have transactional data of customers. So let's see how many rows our data frame has. And we see that there are 69,734 rows. And then I want to check exactly how many unique users or how many unique customers I have in my data frame. And for that, from the casino data frame, I'm first subsetting the customer column, and then I'm applying unique to only get the unique values. And I see that what I'll actually have to do is move from this data frame of transactions, which has 69,000 rows, to a smaller data frame which only contains 2,280 rows, 1 row for each one of the customers. So then each row is going to encode features of the customers, and these features are going to have to capture the behavior of the customer. So in cluster analysis, what we are actually doing is, based on the features of the customers, create groups such that the similar customers are close together within the same group and the different customers are far apart, belonging to different groups. If you've already familiarized yourself with cluster analysis, maybe you've come across terms like within group variability, which has to be small, and between group variability, which has to be large. Within group variability is small when similar customers are close together in the same group. Between group variability is large when customers that are different are far apart. So the clusters, the groups, are different from each other. As input to our clustering algorithm, we are going to provide the features of the customers, and then the output is going to be one label for each one of the customers indicating the group to which it belongs. But we don't have customer features, so let's build them. And this process is called feature engineering. When it comes to feature engineering, the way that you are engineering the features is different for each one of the use cases. But for this particular clustering problem, what I think about, or how I think about it, is if I were to characterize each one of the users based on their behavior, what questions would I ask? So the first question that I would ask is, what's my history as a company with that particular user? Or how long has been the person a customer for? Is it an old customer or is it a recently acquired customer? So let's go on and answer this one question. I can count the number of days since my customer purchased the first time, or since the customer deposited money on the platform first. And for that, I need a base timestamp. And given that the last observation or the last date in my dataset is the 29th of February 2020, I'm going to set the base timestamp to be the 1st of March 2020, so one day after. And then what I need to do, because I want to check for each one of the customers how long have they been a client for, I can count the number of days since the first deposit. First of all, I'm going to group my data by customer because I need to calculate one number for each of the customers, and that number is going to be the number of days since the first deposit on the platform, and then I'm going to aggregate the timestamp. That means that for each one of my customers, I am going to calculate which is the first day when they deposited money on the platform, and then I'm going to subtract that date from the base timestamp, which is the 1st of March, and I'm going to report the number of days in between these two dates. And afterwards, I'll store this information in a new column, which I call first active in days, or like first activity in days. And I can see over here that I have added a new column to my customer data frame, and here I only have 2280 rows, which matches the number of unique customer IDs that I have. So for each one of the customer IDs, I have actually calculated how many days ago they became a client or a customer. Now, the next question that I would like to answer is, when did the customer purchase last time from my platform? Or how recent was the last purchase of the customer? And for that, I don't have to change very much this equation over here. All I need to do is actually change the minimum over here to maximum, because now what I'm comparing is the base timestamp against the latest purchase, which would be the maximum date that I have in the data frame for each one of the customers. And then now I'm going to replace the name of the column over here to be the last activity in days, and then run the grouping by once again. This is going to yield a second column, but this time I'll have the recency of the purchases. So the most recent, the last purchase, the better it is. The first customer over here purchased last 2 days ago, but customer 1000 over here purchased last 300 days ago. So of course, the most engaged the customer is, the better for the business. So you would like to have a low number here in last activity in days, and also a high number here in first activity in days, because here what you are actually counting is how many days ago did they become clients. And then the third question that I would be interested in is, how much does each one of the customer buy from the platform? so the number of purchases. And given that up here I have a transactions data frame, which I'm starting from, the casino has one transaction on each one of the rows, everything that I have to do is group my data frame by customer once again, and then count how many timestamps I have for each one of the customers. And that's going to give me actually the number of times a customer transactioned or deposited money on the platform. How can I do that? Well, I can simply add over here another column that is going to be called number of purchases, for example, and then under number of purchases I am going to just count the timestamp rows. And running this again to obtain my first set of engineered features. Two of the features that we've engineered over here are based to a recency, frequency, monetary value model, which is also called RFM, and it is often used in segmentation of customers for marketing purposes. So R stands for recency, and we have the recency over here in last activity in days. Then F stands for frequency, or how many times the customer bought from the platform, and we have here the number of purchases. And then what we are left with uncovered is the monetary value, or how much money did the customer spend on the platform. So then let's also cover this topic of monetary value, and let this be the next question that we are actually trying to answer. So how much money did the customer spend on the platform? Once again, we need to group our data frame by customer and then get an aggregated measure for each one of the customers. So we are going to aggregate the amount of money, and we will just sum up for each one of the customers the amounts that were deposited for all the transactions that the customers did on the platform. And this is going to be the monetary component of an RFM model. But what's more interesting, I would think, is how much diversity there was in the amounts transactioned by one user. Is the user used to always deposit the same amount of money, like $10 or $50, or the money that the customer deposits varies highly? So it might be that sometimes they deposit $10, and which is the minimum on the platform, and then some other times they deposit $500 or $2,000. And for that we are going to calculate the standard deviation. Let's check how this data frame looks like. And we can see over here that we have a customer, which is a group by column. So this is the column that we grouped by. So let's reset the index and bring the customer back up as a regular column. And over here now we have the two headers of this data frame, which is a bit unusual. So what we will have to do is actually drop this first header. Now let's see exactly what happens when we drop headers. If we use here drop level 0, we are going to drop the first level, so the uppermost columns. Let's see how that looks like. So we are only going to preserve the second header of the table, which is some standard deviation and no name for this customer ID column. But that's not a problem because we could rename that. But if we drop level 1, then we are actually dropping the second row of the header, and we are left with customer and then 2 times amount. But actually these two columns are not representing amount. So one is the total amount and then one is the standard deviation of the amounts. So these should also be renamed, but probably it would create more confusion. So let's just drop the level 0 columns. Let's use this chance to rename our columns. Let's specify over here in place equals to true, because this way we are just going to replace directly within this data frame. Okay, and now over here we just have created our second group of engineered features. Another question that I would ask is related to the behavior of the customer monthly. So for example, how much does a user spend every month on the platform? To answer these questions, I would have to aggregate my data, not just by customer, but also by month. And then I would get a data frame with the amounts deposited on the platform each month for the customers. And then I would be able to actually compute the average monthly amount. So let's do that. First of all, we are going to create a new column in our transaction data frame. So in Casino, we are creating this variable called yMonth, where we store the year and the month of each one of these transactions. So we've just created this variable from the timestamp variable over here. And now, as I said, I will have to group my data by two columns. So first of all by customer, and then also by this newly created variable which is called yMonth. And then, because I'm interested in calculating the total amount of money deposited on the platform during each one of the months for each one of the customers, I'm going to use sum. But before that, I am going to specify which of the columns do I want to be summed up. And that's going to be amount. This is the group by element, and now we are going to reset the index to have everything very nicely looking. And we can see here that for customer 1, in each one of the months we have the total amount that was deposited on the platform. So now what we need to do in order to calculate the average amount, we are going to calculate the mean for each customer. So we are going to group by again this newly created object, but this time only by customer. And now we have this new object which has once again 2180. And now we have this new object which has once again 2280 rows, one row for each of the customers, and then it has the amount of money, which is the monthly average that each one of the customers has deposited on the platform. What we'll need to do next is rename this column in order to be more indicative or descriptive. So monthly average spent. This is going to be the third group of engineered features. Now what we will need to do is put all this information together in a new data frame, which is going to contain 2280 rows, so one row per customer. And to do that, we'll need to first reset the indices on all three of our smaller data frames to be customer. And after resetting the index, we can use the join method, and we are going to first specify which is our base data frame, and then with join within a list, if we have multiple data frames that we want to join to our base data frame, we can just specify the names of those secondary data frames. And we are going to reset the index, and now we can see that we have one data frame which contains all the information or all the features that we have previously engineered. If you've enjoyed what you've seen until now, please hit the subscribe button and be a member of this community, and then we are going to proceed with performing cluster analysis. One thing to keep in mind when performing cluster analysis is that none values are not allowed. So first of all, let's check if our dataset has some missing values, and we can use that with customer data is none. And here we have a data frame with the boolean for each one of our values. And now if we just calculate the sum, it is going to return the number of missing values that we have in each one of the columns. So we see here that at standard deviation there are 845 missing values, and this is based on the previously performed exploratory data analysis, because there are customers who only have one transaction. It is impossible to calculate a standard deviation for only one value, because there is a need for at least 2 data points in order to calculate variance and then a later standard deviation. And what we can do in order to actually mitigate this problem is to replace the non-values with a different value. It could be 0, it could be a very, very small value if we are planning to do some log transformations on the data, because we cannot take the log of 0. This time we are going to replace the values with a very small value. At each position where there is a missing value in the column standard deviation, we are going to insert a 0.001 value, so very small value. And now we can proceed with creating a pair plot of our features. So we are just going to input the customer data, so all our features. So first of all, we have here the sum, which is the total amount of money spent on the platform. And we see here that actually this is a very skewed distribution. If you can see, this is a histogram, but it's highly skewed to the right. And there is an outlier visible up here, which is a person who probably deposited a very high amount of money. Then we are looking at the standard deviation, at the dispersion of the transactions for each one of the customers. This is also a very skewed distribution, also skewed to the right. We are seeing over here that the first activity in days and the last activity in days have a cutoff, and that's normal because 0 can be the minimum number or 1 can be the minimum number, so this cutoff is very visible also here on the scatter plots. And then we have the number of purchases. So what we see actually is that our distributions for each one of the variables are very skewed. We can try to cluster these data points as they are, but it is very unlikely that we are actually going to get some significant clusters from these variables. So what we could actually do is try to do some data transformation before. Okay, but just for the sake of it, let me first just run a cluster analysis on this data set and then do the transformation and check if there is any difference. First of all, I am going to select the features. So from my customer data, I'm going to only select those columns that I need as the features. So this is going to be our input feature in the clustering algorithm. And now in order, because we don't know, we have no idea how many groups there might be in our data set. There is no indication of different groups from the pairs plot. And so we would need another method in order to accurately select the best number of groups. We are going to actually run like a grid search. We are going to run KMeans cluster with different number of groups and then look at the within cluster sum of squares and assess how many groups we need based on this measure. This is also called the elbow method to select the optimal number of clusters. So first of all, let's define a cluster list which is going to contain the number of clusters that we want to perform our experiments with. And we are going to iterate over this list with a for loop. For I in this particular cluster list, we are going to initialize the KMeans clusterer, and inside the KMeans we can pass in different parameters, and one parameter is actually the number of clusters. This number of clusters is going to be different at each iteration. It's going to be I, KMeans.fit. So this is actually just training the clustering algorithm, and we are going to give it the input features. After training KMeans on our features, we are going to extract from KMeans the inertia, and the inertia is nothing else than the within cluster sum of squares, or how different are the points in the clusters that were inferred from the data. And this is going to be the measure of interest. So let's say this is the within cluster sum of square. And now we will need to append this measure for each one of the iterations to a list of within cluster sum of squares in order to have the history of cluster and within cluster sum of squares. Okay. After we have done that, we now plot the numbers belonging to each one of the clusters. And here is the elbow method. The number is decreasing with the number of clusters, and we can choose that number of clusters for which the within cluster sum of squares is not the lowest, but the point where this elbow is being created. So here from this data, it seems that the optimal number of clusters would be either 2 or 3, but probably 2 would be better. Now let's look at the silhouette plot for different clusters in order to see which is the quality of clustering, because this is a method that is analyzing the cohesion and the separation of the clusters. And we can see over here that with 2 clusters there is one dominant cluster, then over here there is a very tiny cluster with very few data points. So this is not going to be optimal to choose 2 clusters. First of all, because the score, the silhouette score of this very tiny cluster is not above the overall silhouette score that would indicate good separation between the clusters. And this is actually what we are looking for. We are looking for a situation in which all the clusters, or the majority of the points of all the clusters, are above the silhouette score, because this would indicate a good separation of the data points in each one of the clusters. And as we can see over here, it is not the case, not even with 9 clusters. So what's left to do now? As I told you before, given this pairs plot, I'm not very surprised that our algorithm is not able to capture any patterns in the data and cluster optimally. So what I would suggest doing in order to add some spread over here, because all the points are really concentrated around these very small values, it would be to logarithmate the data. So we are going to benefit from the fact that here we did not set the missing values to 0 but to 0.001, because we will now be able to use the logarithm. From the NumPy package, use the log method and pass in our variable. And now let's say this is going to be log std. Okay, now let's check over here, input the std variables. How would they look like? Would their distribution look more normal and less skewed? Okay, let's check that. So this is a very big difference that the logarithm has brought to our data points in terms of distribution, but also we can already see that there are some separations over here. So here, for example, I can identify at least 2 clusters, but there might be some clustering of this cloud point over here as well. Let's check now if we've logarithmated our data. Would the elbow method indicate a different number of clusters or not? And indeed, we can see over here that the elbow method indicates that the perfect number of clusters would be 3. And now let's also change here the input to be the STD, which is the logarithmated values. In the silhouette plot, imagine these are like very, very thin bars. So it is like a bar plot. And the bars are corresponding to each one of the data samples. So each one of the data samples has a particular score, which is called a silhouette score. And that indicates how good that particular point is clustered, or how similar it is to the other points within the cluster, and how dissimilar from the other points in other clusters. We can see that the silhouette score can range also under 0, so it ranges actually from -1 to 1. The lower the score gets, the worse that data point is clustered. So with the negative data points, these are actually outliers. The goal is that actually the scores of each one of the data points go beyond the overall silhouette score. And then we can say that the clustering was successful and it is very meaningful. With two clusters, we can see that there are data points that go beyond these overall silhouette score in both of the clusters. With three clusters, that is not the case, because this red cluster actually doesn't have any of the data points going beyond that silhouette score. So it might be that the data points over here are overlapping with other cluster. You can see over here that, for example, with 5 clusters, the silhouette score is much lower, under 50%. Under 50% is poor clustering, and then all of the clusters go beyond this silhouette score. But again, this means poor clustering, so it doesn't matter that the points are going beyond the score, because the score is very low. And the more clusters we add, the lower the overall score. So let's then limit ourselves to 3 clusters, and we see here that the overall silhouette score is almost 50%. That's decent. Add a new column to our customer data, which is called group, and this new column is going to contain for each one of our customers label mapping to the group the customer belongs to. So we see over here that customer 1 belongs to group number 2 and customer 1001 belongs to group number 1. So these would be customers from different clusters, different groups. They should be treated differently if the clustering makes sense. And now let's visualize with some scatter plots how well our clusters are separated. First, let's look at the scatter plot between the standard deviation, which indicates how different or how much the amount of the transactions diverge from the average, against the average amount spent every month. And we can see over here that we have indeed 3 clusters, 3 groups. One is very well separated from the others, and then the other 2 clusters are overlapping over here in the middle. If we would like to get a picture of what makes these clusters different, we could not, because the values we have on the x-axis and on the y-axis are actually logarithmated values. So how do we bring back these values to the normal regular values, but at the same time without compressing all the data points as we have seen previously they were in the pairs plot? So we have a step of 2 between each one of these axes, and then we are going to build a list where we are going to store the reversed values of the logarithm, and then for each value I in the range, and here we are going to take exactly the range we have over here, from -4 to, let's say, 8, and then this range is by 2. We are going to calculate the reversed value, which is going to be, we will round it, but it is going to be the exponential of the I value, and we are rounding it to 2 decimals, and then we append it, and then we have a set x tick labels, the labels at each tick point, Okay, and we see that this is a little bit shifted, so we will need to add a 0 over here. And now we have the correct distribution. So we have here, over here, we have those points for which the standard deviation is 0. And you remember we've previously said that it is not possible to calculate a standard deviation if we only have 1 point. So actually these are all those customers who have only deposited money on the platform once. And then in this second group with pink points, we have those customers who have a higher variability in the amount that they deposit. And with the black points, we see that the variability is even larger. But now these two clusters seem to differ based on the monthly average amount that they spend. But again, we do not have a really good representation of this average amount spent. So let's convert it from a logarithmic scale to a regular scale as well. And we are going to use exactly the same approach as before, but this time we are going to refer to it as the Y scale, as the Y label. And now we will have to change the range over here, which goes from 2 to 11, but it is by 1. So the step is of 1, and then it goes from 2 to 11. And then we will have to also display it on the graph by using the set ytick labels as Y. And we can see over here now that indeed there is a minimum amount that can be deposited on the platform, that is $10. And then we have this group of people, the pink ones, that are usually depositing lower amounts of money, so up to maybe $1,000, the larger amount. And then there are these black points over here in the third cluster, which are gambling amounts which are much larger, and also the variability of the amounts deposited is larger. These are our three clusters. Let's do the same for the standard deviation and the sum. And we can see again that there is a much clearer separation between the two clusters now. So the standard deviation indicates again the spread of the sums transacted, and then the sum is the overall amount of money deposited since the customer first started to deposit money on the platform. We have that cluster where people only deposited money once and then they stopped using the service, and then we have the customers which are gambling or which are transactioning really high amounts of money. But also the spread of the deposited amount is very large, and there is more variation for these customers compared to those who are only depositing lower amounts of money. For now, so let me know in the comments if you would like to dedicate a video to advanced feature engineering for this dataset in particular. I've thought that maybe it would be interesting to check whether the users also play on the weekends or just on the weekdays, whether they play during night hours or not, or which are the time windows they are most active in, what's the maximum number of days with no activity between their rounds. These are all features that you could actually just implement yourself and see if they would bring improvements to the clustering algorithm. If you've enjoyed this hands-on tutorial and would like to explore more applied data science topics in the future videos, I invite you to subscribe to the channel and join my growing community of data science enthusiasts. Thank you all for being here and for subscribing to the channel, and I hope to see you next time.